kind introduction. And yeah, as the title suggests, I want to talk a bit about how we can use dimensional regularization in asymptotic safety or asymptotically safe quantum gravity. And to motivate this a bit, I want to start with talking a bit about dimensional regularization itself. And as you probably all know, dimensional regularization is sort of the gold standard in particle physics or in computations that, for example, led to the prediction of the Higgs particle in the standard model. And there's a few reasons why dimensional regularization is so successful or so powerful. And one of the biggest advantages that it has to offer is that it complies with gauge symmetries, like an abelian or non-abelian gauge symmetry, gauge theories, and also diffeomorphisms as you encountered in quantum gravity. And also by now there's like a large set of tools available that really allow high order perturbative computations in quantum field theory. And for example, a few years ago, the 5-loop beta function QCD has been computed. And I think in scalar field theories, it's up to 7-loop. So there's really a lot of technical tools available. And together with the preservation of course, the preservation of gauge symmetries also allows for those tools to be available to such high orders. And this is why dimensional regularization is really one of the core regularization methods in QFT. And you might be wondering, what about asymptotic safety? Because it doesn't play apparently such a big role in asymptotic safety in our field. And you might be wondering, or I want to explain a bit why I think that might be the case, even though actually one of the first pieces of evidence that we have for asymptotic safety was actually derived or we got from dimensional regularization by a continuation from two-dimensional spacetime. So this goes back to work in the early 90s, and it's the idea that gravity in 2 dimensions is actually asymptotically free. And when you then extrapolate to a positive epsilon, you will get a non-trivial fixed point. And the 1-loop beta function that gives rise to this, so for Newton's coupling, is shown here. And you see that B1, which is a positive number, together with a positive epsilon, will lead to a non-trivial fixed point in the UV. And in this way, you can see that, or you have some pieces of evidence for this asymptotic safety scenario based on dimensional regularization. But of course, this also, this approach actually has some little subtleties included, and this arrives largely from the propagator. Of course, one non-trivial subtlety is, first of all, the extrapolation that you have to do to epsilon equals 2. And it's non-trivial or non-trivial question to ask whether this is actually still within the range of convergence that you would expect, or whether it's even as an asymptotic series in epsilon would be a good thing to do, or setting epsilon to 2. But even apart from that, you also have the problem that the propagator, and here I'm showing the flat propagator, obtains a pole in d equals 2. And this comes from the fact that gravity is topological in 2 dimensions. And sorry, one sec. And this leads to the epsilon 1/epsilon pole that you can see in the flat propagator. And this has basically 2 problems that come with it, or 2 pathologies. One is that you can misidentify this 1/epsilon pole that comes now from the propagator as a UV divergence. And you can also see that basically because of this kinematic pole in the propagator, you get potentially non-local divergences at 2-loop that would require, of course, non-local counterterms that are not usually present in a quantum field theory, and would be, from a perturbative perspective, a bit surprising to have that in a quantum field theory of gravity. And so with these sort of like issues in mind, so the extrapolation to epsilon equal 2 and this kinematic pole in the propagator, I want to ask a bit whether we can just directly use dimensional regularization in 4-dimensional quantum gravity to see whether we have a fixed point in the sense of asymptotic safety. And so to talk a bit about whether or not this is possible, I'm showing you here the general form of the 1-loop beta functions in quantum gravity. And so we have the cosmological constant here, which is lambda, and Newton's coupling, which is g. And then you can show that at 1 loop, This is basically the general form that you'll get. Of course, I'm neglecting off-shell divergences here in the form of quadratic curvature invariance, but apart from that, this is the general form that you see. And this, of course, has a very particular structure, namely that these higher order or the one loop corrections that we have included here, which is like this term here and this term, they're all higher powers in or higher orders in G Newton or Newton's constant, because this is the perturbative parameter of this theory in this case. But one loop does not just generate you one contribution to the beta functions, but instead you have like various contributions that come from the structure of divergences that you have. And for example, you have logarithmic divergences, which are these blue terms here. You have quadratic divergences and quartic divergences even for the cosmological constant. And while these are generally present in this general answers for the one loop beta functions of quantum gravity, it happens that if you use dimensional regularization with minimal subtraction, actually only the logarithmic divergences are present in the beta functions. So in this case, my factors of A1 and A2 as well as B1 are set to 0, and you obtain these beta functions here. And then you can see that you can only possibly have a fixed point if A3 is just negative B2, because you have effectively just one coupling, the product of G times lambda, that you can choose to have a fixed point. And because in general, A3 is not equal to minus B2, you see that there's no one loop fixed point. But I want to ask a bit in this talk, or that will be one of the main questions here, whether this fact that the power law divergences are 0 here, so the quadratic and quartic divergences, does this result from a general property of dimensional regularization being blind to power law divergences? Or is there something more to it? Is there something we can do to, even in dim-reg, get back these power law divergences and then have a one loop fixed point in gravity? So the outline of my talk is like roughly structures in this form. So I start with some general remarks about this sort of perturbative approach that we can do in asymptotic safety. And then I talk about how power laws are incorporated in dimensional regularization. And I will also talk a bit about the dimensional continuation of quantum gravity, which comes back to the kinematic pole that we saw already in 2 dimensions. And then in the end, I will apply this at one loop to quantum gravity to see whether we can actually find a fixed point or not. And I will conclude at the very end. So this perturbative approach that I want to like lay out here a tiny bit, the idea is just that you start from the gravitational action, and at tree level, you basically just have the Einstein-Hilbert term. But of course, we know due to the non-renormalizability of quantum gravity that you have to include various higher order terms that will be required to renormalize higher order divergences that you will encounter. So at one loop on shell, you are only required to take in the Euler term. So that's just a topological term. And for that reason, pure quantum gravity, as you can sometimes state it as one loop renormalizable. But then starting from two loop, you need more counter terms, and they are not vanishing on shell, and they're also not topological, like the Gorov-Synodic term here, which is written down here. And then, of course, you will get more and more terms if you go to higher loop orders. But I don't really want to talk about much about what you do with these higher loop terms here. I just want to focus about the Einstein-Hilbert sector, basically. And then the perturbative approach that we could try to do to study quantum gravity is that you see this as a perturbative series in Newton coupling, and you calculate various Feynman diagrams. And depending on what observable you have, you would put various external x to all of these diagrams. And then you can see what values we get for those observables. But of course, as in almost any quantum field theory, you will see that there are UV divergences, and we require a renormalization of couplings to absorb these. So we first have to regularize these loop diagrams so that we get a regulated result, and then we have to absorb the divergences that we see in a renormalization of the couplings. And this, of course, leads to a running of couplings, as I've already shown you before, and with this general form at one loop. And we already, or I already said that these power law, if you don't have power law divergences, you generally don't have a one loop fixed point. And therefore, we want to see whether by the inclusion of those polar divergences, we can achieve a fixed point. And of course, there's various different ways to obtain those beta functions. And I just want to show you a very brief overview of 3 different ways how we could regularize in integrals or divergent integrals in quantum field theory to renormalize the couplings afterwards. One of the most basic ones, of course, is the momentum cutoff. So the idea here is just that you suppress or you cut off the momenta in the UV by some renormalization scale k. And then you will get finite results because these integrals that on the left-hand side here, so this integral would diverge quadratically, would not diverge anymore because you just cut off with a hard cut off the UV modes of this integral, and therefore you get a finite result. And of course, the main regularization of this talk is dimensional regularization, which works very differently compared to the momentum cutoff, namely that instead of cutting off any momenta, we just deform this integral such that we get a d-dimensional integral. So this Jacobian that you get usually in 4 dimensions would be p to the power of 3, so where p is the momentum, is now d-dependent. And then you can see that if you analytically continue to smaller d's, you will regularize the UV divergences that you have on the left-hand side. And in this way, you can use this continuation in the dimensional parameter as a regularization of a quantum field theory. And this is this powerful method that we want to use here and has been, or is mostly used in particle physics. There's also another interesting regularization that I want to mention briefly, and that's the Schwinger proper time cutoff, or more generally, you would, or this is sometimes called the operator regularization. And the idea here is that you have the propagator and you write it with the Schwinger parameterization in this exponential form. And then the UV divergences you can regularize as this lower integration limit that I've introduced here. So K is the UV regulator here. IR divergences would be found in this upper limit. And one of the nice properties of this regularization is that if you write this for the full propagator, so by going into the background field method, and you have the full propagator here, not just a flat propagator that I have written here, then you can insert the heat kernel here and you obtain a regularization that is also respects the symmetries of the theory. So it is gauge invariant and diffeomorphism invariant, like dimensional regularization. And this is, of course, a big advantage compared to the momentum cutoff. And I just wanted to like briefly mention these different regularization schemes here. And the reason why I'm introducing these, apart from dimensional regularization, is that I want to understand a bit better what or how polar divergences show up in quantum field theory. Because for momentum cutoff and also for the Schwinger proper time cutoff, because it's essentially also a cutoff regularization, it's kind of intuitive how you can see these quadratic or quartic divergences showing up. And now I want to basically just use some sort of cutoff regulator that can be now the momentum cutoff or the Schwinger proper time cutoff. And I want to see what my general form for the one loop renormalization of Newton's coupling would look like. And I'm going to do this here with some sort of minimal subtraction applied to this cutoff regulator. And then the general renormalization for Newton's coupling. So on the left-hand side, I have the bare coupling G naught. And on the right-hand side, I have the renormalized coupling. And the structure that you see here is very, very similar to what we already saw for the beta function of Newton's coupling. Namely that you have some one quadratic divergence for Newton's coupling and a logarithmic divergence. And I have introduced here already the cutoff scale K, which I use to regularize the momentum integrals or the Schwinger proper time integrals, if you want. And I have introduced the sliding scale mu because I need to introduce the sliding scale mu to make the argument of the logarithm dimensionless. But I don't have to introduce anything depending on mu for the quadratic term here. And this is interesting because typically when we do perturbation theory, we obtain the beta function by the dependence of the sliding scale. So we use the fact that the bare coupling G naught has to be independent of the sliding scale mu. And then you see, you can derive that the beta function that you obtain for the dimensionless Newton's coupling, so my small g is the dimensionless version of this big G, the renormalized coupling. And you see that you get this term or this form for the beta function. And what's interesting here is that because we use the minimal subtraction scheme where the quadratic divergence does not have any dependence or any additional dependence on mu, we actually do not see the quadratic divergence here. So we only see the logarithmic divergence, even though we have used the cutoff regularization. And this kind of happens because we use the sliding scale here, and we use a minimal form of the subtraction for a cutoff. But of course, there's different ways to do this, and you don't have to follow minimal subtraction. And one way that you can see this quadratic divergence in this cutoff regularization is by following a scheme that was used by Max Niedermeyer already in one-loop computation of quantum gravity, where he proposes that the sliding scale evaluated at the UV cutoff k should lead to the renormalized and the Baire coupling being equivalent or equal to each other. And of course, this is very inspired from a Wilsonian picture where the renormalization scale, that in our case is mu, should correspond to a cutoff in the UV. And if you do this, then because of this extra condition that you put on the renormalization scheme, you see that there's actually now a second term or a new term in the quadratic divergence. And this is this mu squared. And this is just to ensure the fact that if you set k equals to mu, then the logarithm drops out and this quadratic divergence drop out. And then you see that G naught is, as this renormalization prescription tells you, G naught is equal to G. And because of this mu square term that we have now on the Baire coupling, or the renormalization for the Baire coupling, we actually get now dependence of the beta function on the quadratic term or the quadratic divergence that we see in the regulator. So what the bottom line of this is, what I showed you on the last two slides, is that, and this is more general than in dimensional regularization, but to obtain power law divergence or a sensitivity to power law divergence and perturbation theory, we require some sort of non-minimal subtraction, and we cannot just use minimal subtraction. Because in minimal subtraction, as I said, that there's no mu squared dependence, and the dependence on the power law divergence will drop out. And I've shown you this here for the quadratic divergence, but of course this also applies to quartic divergences and any form of power law divergence. And then a very natural question to ask, I think, is whether we can also find such non-minimal renormalization schemes applied to dimensional regularization. Because if I can use the cutoff with a non-minimal subtraction to see power law divergences, then I might be able to do the same with dimensional regularization as well. And this brings me to this next little part of the talk, namely power law divergences in dimensional regularization. So basically, the task that we have set for now is that we, when we look into this general ansatz for the renormalization of Newton's coupling now in DIMREG, we want to find a renormalization scheme that gives us a non-trivial value for this parameter B1. So as before, this B2 is a quadratic divergence, and you see that it has the dependence on the cosmological constant as in the cutoff scheme. And then the quadratic divergence does not have any dependence on the cosmological constant, but just this mu here. And for dimensional reasons, this first term here must have 2 powers of mu more, which is just like a fact that it relates to quadratic divergences. So the goal is to find such a non-minimal scheme that fixes B1. Of course, in principle, I think you couldn't come up with any sort of unambiguous method of determining B1. But here, because I want to have this kind of physical picture in mind of having a similarity with power law divergences with a momentum cutoff or any cutoff, I want to see whether I can actually find a scheme that fixes this B1 here in terms of quadratic divergences and higher order power law divergences, coming from a dimensional regularization point of view. And to find such a scheme, we want to see whether there's any way in which we can actually see power law divergences in dimensional regularization. And the answer is yes. And this is actually a well-known fact in the literature, already going back to Feldman in 1981. And the point is that if you have a quadratic divergence, like here on the left-hand side, so the left-hand side is in 4 dimensions, quadratically divergent, then you see that you do not just have a pole in d equals 4, but you have a pole in d equals 2 as well. So if I would have, or the general form, how these power law divergences or the general structure of these divergences really show up is that you have a pole in D equals 4 that corresponds to a logarithmic divergence. But if you get poles in smaller dimensions, then you these basically just incorporate power law divergences that you see on the left-hand side. And the way to see is that just that you always get a divergence in dimensional regularization whenever the mass dimension of the integral is 0. So, and if you would have a logarithmic divergence, then you would have, for example, 1 over p squared plus m squared squared, so that you have mass dimension -4 here. And then you see that you have to put in 4 factors of the p on the left-hand side to get a logarithmic divergence, and this gives you the divergence in D equals 4. But if you have a quadratic divergence, then you have a 1 over p squared plus m squared, and not squared or anything. So the mass dimension of this integral is just m to the -2, if you want to say so. And therefore, you just need 2 powers of the fact of the momentum coming from the integral to get a dimensionless integrand. So in this way, you see that the higher or the power law divergences that you can see on the left-hand side of this equation here also show up on the right-hand side, just basically like seen as divergences in lower dimensions. And this then, so this observation that power law divergences lead to divergence in D less than 4 leads you to the definition of a scheme, which I'm calling here power divergence subtraction. And the idea is just that you will normalize Berg couplings to remove divergences in D equal or less than 4. So if you would follow minimal subtraction, you will just remove divergences in D equals to 4. But this sort of generalization that like basically proposing here to get rid of or to be sensitive to power law divergences just tells you that you also have to remove the divergences in D less than 4. And I'm, of course, as you probably guess, not the first person to come up with such a scheme. And like suggestions for such a scheme have been going back to Weinberg, who mentioned this as a sort of little side note in 1979 already. But then Jack and Jones made some sort of first applications, but in the context of a normalizable field theory, because there, if you have a sort of mass parameter like the Higgs mass, you could also see modifications compared to minimal subtractions coming from power divergence subtraction and such theories as well. But then it was sort of rediscovered 8 years later in the context of nuclear and effective field theories. So there, what people do is that they have some sort of effective field theory for nucleons or the interaction of nucleons. And so they want to understand the momentum expansion of this theory. And for this, they have to, as in typical effective field theory, include like non-renormalizable operators into the theory. And you can then compute this using various regularizations, of course, like dimensional regularization with minimum subtraction or cutoff regularizations. And it turned out that because cutoff regularizations are sensitive to power law divergences, that these have extended validity range for the momentum expansion compared to minimal subtraction. And the same happens if you use this PDS scheme, so the power divergence subtraction scheme. So in this way, a power divergence subtraction really gives you an extended range where the momentum expansion is valid and therefore is an improvement of the theory compared to minimal subtraction. And this, like a term of power divergence subtraction, also goes back to these works in nuclear and effective field theories, where they invented this term to describe the scheme. To have some more or general remarks about the scheme, let me just note that these divergences that we see in D less than 4 are just corresponding to additional finite renormalizations when you set D equals to 4. So they actually don't change the pole structure that you see in D equals 4. And therefore, they don't modify really any poles of the theory, which would be bad because then you would potentially not get a finite result anymore if you go to D equals 4, which you want to do in the end. But because the divergences in D less than 4 are just additional non-minimal subtractions, this is actually a valid defined scheme. And you can also see the general behavior of how loop or power law divergences make themselves known at any loop order L, because I've already mentioned that the quadratic divergences of the Newton's coupling, for example, show up in 2 dimensions. But in general, you have some sort of slightly more complicated dimensional dependence for these polar divergences. And you can show that just by power counting or of writing down some higher loop integrals, that if we go to L loop order and you want to see a power law divergence of degree n, you have to compute the divergence in this critical dimension, which is given by 4. So 4 is just coming from the target spacetime where you want to go to, if you want to say so, which is 4 dimensions in our case. And then you can show that you have this sort of structure for power law divergences of degree n. In particular, at one loop, you see from this formula that quadratic divergences, so n equals 2, corresponds to d crit equals 2. Quartic divergences correspond to divergences in 0 dimensions. And then if you go to higher loop orders, you will get sort of fractional spacetimes that you have to look into because you have more powers of the loop momentum. And this sort of shifts loop order by loop order, the critical dimension where you have to look at. To explain a bit more in detail now how this looks like, or what this looks like for Newton's coupling, if you would look back on the previous slide before where I presented this ansatz for the bare Newton coupling and this non-minimal subtraction, we have still this term here, which is the logarithmic divergence, and this is completely unchanged. But in addition, we have now, from renormalizing a divergence in d equals 2, a second term here. This is B1, and this is the goal that we wanted to achieve before, that we have some scheme that tells us something about this coefficient B1. And because we have now this quadratic divergence, you can see that the beta function that you derive from this bare coupling has now quadratic divergence or dependence on the quadratic divergence. So we are sensitive now to the power law divergence that would show up in quantum gravity. And this is encapsulated by this term here. And of course, this term here is the same as before and not changed at all. And you can also see how this applies now to the cosmological constant as well, of course. So here we have one more additional term of the cosmological constant. So we have a logarithmic divergence in d equals 4, a quadratic divergence in d equals 2, and a quartic divergence in d equals 0. And then you can, in principle, use now the scheme PDS to calculate all of the value of all of these coefficients, B1, B2, A2, A1, A2, A3, and determine this renormalization for the couplings in this non-minimal scheme, and you obtain a set of beta functions. And because you have now a sensitivity to power law divergences, you can, even using dimensional regularization, find potentially beta functions that can exhibit a one-loop fixed point, because B1 in this case is non-zero, and the other coefficients A2 and potentially also A1 can principally be non-zero. And you might be wondering now, why should we care about dimensional regularization? Is this just like some sort of academic problem that I'm trying to that I'm talking about here, of seeing whether we can use dimensional regularization in principle to see fixed points, or is there something more to it? And I think there's something more to it, namely because of these advantages that dimensional regularization has to offer compared to other renormalization schemes that I talked about in the beginning. This is why it's so powerful in particle physics. Namely that DIMREG respects almost all symmetries of quantum field theory. In particular, it respects gauge symmetries, including non-abelian gauge symmetries and diffeomorphism invariance. And it allows expansions to higher orders in perturbation theory. And these two properties are actually not that easy to fulfill in other regularization schemes. Of course, in principle, you can use momentum cutoffs. And the problem with them is that they do break gauge invariance. And this also includes, for example, one-loop approximations of the FRG. So they break gauge invariance or diffeomorphism invariance. And therefore, you require additional counter terms to restore the symmetry. And if you look into that, especially if you would try to do this approach at higher loop orders, this becomes complicated very, very quickly. And for practical purposes, I think that's not very useful to do. You could also try to come back to this Schwinger proper time cutoff, or more general forms of this in terms of an operator regularization. because as I said, that they do respect gauge invariance, at least at one loop, and because they can, within the background field method, at least formulate it in a way that they do not break any gauge or diffeomorphism symmetries. But the problem with this approach is that you generally have, or it's non-trivial to generalize this to higher loop orders. And in fact, I don't know whether it's possible to make some sort of general attempts to apply this to second loop order or higher loop orders. And the problem that arises here is that if you work in the background field method, which you want to do if you want to have a gauge invariant form of this Schwinger proper time cutoff, then in the background field method, you would regularize, or you would compute one loop divergences by a logarithm of this one loop integral. And two loop divergences are just like higher order integrals, and they depend not on the logarithm of the propagator of the theory, but on the inverse of the propagator. And there you see some, like basically two different regularizations that you have to perform. And it's not trivial at all that you have a consistent regularization that renormalizes the one loop and the higher loop terms in a consistent fashion. So for that reason, I think that dimensional regularization is really powerful here and could allow something that other regularization schemes would only, or it would only be possible with very difficult methods to, namely that you can explore asymptotic safety and quantum gravity to higher loop orders. So you can do one loop computation, which is what I'm going to talk about later in this talk, but you can extend this in principle to higher loop orders, which I think is really exciting if you want to get some sort of perturbative evidence for fixed points in gravity. And so with this now, we understand a bit how we can see power law divergences in dimensional regularization. But I've already mentioned that the quadratic divergences actually depend on the divergences that we see in two-dimensional space-time. And now you, of course, can come back to the problem that I kind of started with in the talk, namely that in this dimensional continuation that you do from d equals 2 plus epsilon to four-dimensional space-time, you have this problem of the kinematic pole in the propagator. And this problem will in principle, or could in principle also show up here. So because PDS requires the computations of any divergences in d equals less than 4, we have to be careful that we don't fall into the same problem of kinematic poles in d equals 2. But then you can ask whether there's actually a way to avoid this kinematic poles in d equals 2 using PDS. And the way I want to think about this here, or the advantage that we can do in this case, because we want to basically view a power divergence subtraction as a regularization for four-dimensional quantum gravity, is that we can modify the dimensional continuation of gravity to obtain finite results also, or to obtain a finite propagator also in d equals 2. And the way I'm thinking about this is that in principle, and this goes back to this perturbative approach to asymptotic safety, you just want to compute these sort of loop diagrams. So you have a one loop integral, two loop integrals here, and you just want to find a way of prescribing a finite value to all of these diagrams. And this is the goal of a regularization procedure, right? And the standard way to do this is that you would start from a four-dimensional theory here, which is the Einstein-Hilbert term. And then on the level of the action, you basically dimensionally continue it to d-dimensional space-time. And then you would basically get the exact same problem in PDS as you saw in d equals 2 plus epsilon, so in this dimensional continuation approach to quantum gravity, namely that you get kinematic poles in d equals 2. So you would get kinematic poles in the quadratic divergences. But you can actually do something different than this. And this idea is that you do not start from the action of the theory and continue to d-dimensional space-time, but you actually derive your Feynman rules, so your vertices and your propagator, from this four-dimensional Lagrangian. And then once you have derived the propagator and the vertices, you perform a dimensional continuation of these objects. And this can actually lead to different results for a propagator, or can avoid this problem of the kinematic pole for the propagator. So for the vertices, actually nothing really would change because there's no explicit dimensional dependencies in the vertices. But for the propagator, this so the fact of where you start to do the dimensional continuation can give a different result and get rid of this problem. And to show in a bit more details, what I mean here is that I'm just computing or showing you here the result for the Hessian of quantum gravity. So I'm just assuming an Einstein-Hilbert action in Feynman gauge. And then you can see that the Hessian of that you get from this theory is having this form where you have some sort of squared covariant derivative and some anamorphism parameter. The exact form is not really important here. But the important piece that you have here is this matrix K, which K has this form. And in four-dimensional spacetime, K is actually its own inverse. So you can then see that the propagator, if you use the Schwinger parameterization to rewrite the inverse of this term here, you can see that the propagator is having this form where you again have the matrix K. But the problem, of course, is that in d dimensions, if you would have started with a Lagrangian in d dimensions, you would not have a factor of 1/2 here, but you would have a factor of 1 minus d2 in the inverse of K. So in this term here, you would see that you pick up the kinematic pole again. And what I'm now doing here instead is that I don't start with the Hessian and perform a dimensional continuation of this term, but I just invert the Hessian to get the propagator. And if I'm in 4 dimensions, this K is finite because there's no 1 over d minus 2 because I already set d to 4. But then I can, based on this, perform a dimensional continuation and actually fix the form of K in any d. So K will always have this form in any d, and I will not write any 1 over d minus 2 terms here anymore. And this will then avoid the kinematic pole that you see in two-dimensional spacetime, and it will still be diffeomorphism invariant because I have written the propagator in a form here. I should actually go over to this slide. So I've actually written the propagator in a form here which maintains gauge invariance, and it's also equivalent to the propagator that you get in 4D. So in this way, you get a sensible dimensional continuation that avoids the kinematic poles. There's only a slight modification or a slight subtlety that you have to look out for, namely that you want to make sure that the propagator is a symmetric matrix in any D, because otherwise you would get potentially unambiguous of whether you contract or you connect a propagator from in a diagram from the left to the right or from the right to the left. And to avoid these ambiguities, you need a propagator that is symmetric. And you can show, and this is what you basically can see, because here it's a bit difficult to see whether this propagator is symmetric even in d equals 4. But you can basically show this by looking at the Hessian and seeing that the Hessian is symmetric. And by working with the Hessian of this dimensionally continued propagator, you can see that you actually have to only slightly modify the anamorphism and give the anamorphism a non-trivial dependence. And in this way, if you just write instead of a factor of 1 here, which is what you get in 4D, you write this factor of 6 minus d over 2. And this way you have as retained a propagator that is symmetric in any d, and it's also avoiding the kinematic poles that you see otherwise in the standard dimensional continuation of quantum gravity. And so in this way, we are basically set now to perform a first exploration of this idea to one-loop quantum gravity, because we have dimensional regularization with a scheme that is sensitive to power law divergences, and we have also formulated a dimensional continuation of gravity that avoids kinematic poles in d equals 2. And therefore, we can use this PDS scheme to see quadratic divergences in quantum gravity and study asymptotic safety. And so all that you have to do is you start.
I have a question, if I can interrupt you. So you're guaranteed that it's diffeomorphism invariant for the background field, but the BRS algebra that is encoding diffeomorphism invariance for the graviton, you haven't talked about the ghosts and so on, but you need them, right?
Yes.
That BRS algebra outside 4 dimensions, if you don't have that d minus 2 factor, I can't see why that BRS algebra would close properly. I mean, the BRS algebra is telling you you've got diffeomorphism invariance of the graviton, and diffeomorphism invariance of the graviton actually fixes completely the kinetic term for the graviton, right?
Yeah. I have to admit, I haven't looked exactly into the BRST invariance here, but I have checked that because one way to see whether you have diffeomorphism invariance or whether you respect the symmetries is you can use the fact that you can calculate divergences for Newton's coupling, for example, from different endpoint functions. So you can calculate it from the two-point function You can also calculate from the three-point function and higher functions. And I've checked that all of these results agree with each other. So in this sense, I guess the question that you're asking maybe is whether this symmetry that I have for the background field also extends in some way to the quantum field.
Yeah, it's a problem that maybe only shows up beyond one loop when you're only doing a one loop calculation. So I guess maybe you don't
I
see
would
it.
not really expect that at higher loops, at least if I stay within the background field method and compute. I've like looked a tiny bit into that actually, and I do see that the renormalization for the cosmological constant, for example, if I compute it at two loop from the one-point function and or higher endpoint functions, that I still get the same result there. But of course, this is all within the background field method, and I don't know exactly what happens if you do this or how this relates to the fluctuation of the graviton or the quantum field of the graviton.
Okay.
But it's
Yeah.
definitely an interesting remark, and I should look into that. Yeah. Does that roughly answer your question? Or?
Thank you.
Okay, thank you. Yeah, so with this like little side remark, I do want to like see what happens if I approach one loop quantum gravity here. And so what we do here now is that we have this action of the Einstein-Hilbert term, and we want to compute simply the one loop divergences here. So we compute the Hessian of this action. I didn't specify this on the slides here, but I'm using Feynman gauge, and therefore I get a corresponding ghost term here. And then what we have to do is we have to compute the divergences in 4 dimensions, 2 and 0 dimensions. And then the result for d equals 4 is corresponds to the logarithmic divergences. So this is actually, these are divergences that are universal, so they are scheme independent. And these are well-known results, I think first derived by, if I remember correctly, Kluth and Feldman, or I don't quite remember. But anyways, these are universal results that are well known for the logarithmic divergences. But I also get now quadratic divergences from two-dimensional spacetime. These are, of course, scheme dependent because they are quadratic or related to quadratic divergences. And if you would find a different continuation of this propagator that I was talking about, you would get a different result here. And but within the scheme that I was talking about so far, namely the specific dimensional continuation of the propagator that I was proposing, and within the PDS scheme, you get this result for one loop quantum gravity in 2 dimensions. And what's actually pretty interesting is that if you go to 0 dimensions, you do not see any divergences. So quartic divergences which could show up in the cosmological constant are absent here. And this is a bit surprising to me. Like I don't know where it really comes from. I mean, apart from a like mathematical point of view, namely if you work with the heat kernel, then you can see that the heat kernel or the trace of the heat kernel for the graviton and for the ghost, so both particles that I'm including here, they are both proportional to the factor of d. And therefore, if you try to see a divergence in d equals 0, so 1 over d pole, this 1 over d pole is just cancelled by this trace of the heat kernel that you include in the computation, and therefore I do not see any divergences anymore. But I don't have any sort of like physical understanding of why this really happens in this game, because in principle, you could have also, as similar to the quadratic divergences, a non-trivial result here. But this is just a little side remark. Now it's putting together these divergences in 4 dimensions, 2 dimensions and 0 dimensions, which are absent. You can determine the general form of the renormalization of Newton's coupling and the cosmological constant. And then you get this result here. And in particular, you get a non-trivial result for the beta functions that contain non-trivial dependencies on quadratic divergences, which are shown here and here. So this is kind of so this quadratic divergence in Newton's coupling is kind of what you would see in these dimensional continuations from d equals 2 plus epsilon, but now with some power divergence subtraction, we have a somewhat different result, but it's kind of the same philosophy that due to this term here, we'll see a fixed point. And this is what I show here. So we do see a fixed point, namely we see in total 3 fixed points. We see a Gaussian fixed point, which is of course always there at vanishing couplings. And then you see a UV fixed point, which comes from this quadratic divergence here. So it's from the divergence in d equals 2. And this leads to a non-trivial fixed point in the UV, which you can see here in the phase diagram. You also get another fixed point at vanishing Newton's coupling. So this is why I call this unphysical. But the bottom line of this here is that with this application of dimensional regularization now, we do find a one-loop fixed point. And we also see that the critical exponents are somewhat similar to FRG computations. Of course, this two that you see here, that's the critical exponents of Newton's coupling. And this is in this one-loop approximation just fixed to 2. So it's not a surprise that you get roughly something that agrees with similar computations from FRG. Yeah, it's just a fixed term here in the one-loop computation. And you also see that if you look on this plot here, you have this separatrix, which is just at vanishing Newton's coupling. I mean, I'm showing the product of vanishing cosmological constant. I'm showing here the product of cosmological constant and Newton's coupling on the x-axis. But the point is that the vanishing cosmological constant is a fixed point here of this RG flow. And this, of course, just comes from the vanishing of the quadratic divergence. So there's no term here in the beta function for the cosmological constant that is just driven by Newton's coupling. So if there would be a quadratic divergence, there would be something like a number times g without any lambda dependence, but this term is absent. And for this reason, I can just like set the cosmological constant to 0 and obtain a fixed point of the beta function for the cosmological constant. So in this way, lambda equals 0 is a fixed point. And so yeah, just small side remarks that I kind of already talked about. So the fixed point is mainly created by the quadratic divergence. So it's this divergence that we see in 2 dimensions. And this is maybe some sort of indication of gravity becoming 2-dimensional, which has been seen in various other approaches, including CDT, for example. So this is, I think, kind of interesting. Of course, this also tells you that one of the drivers of this fixed point is scheme dependent because it corresponds to the quadratic divergence. And then another little remark, which I already talked about, is that the quadratic divergences in the schema are absent. So the vanishing cosmological constant is a fixed point. And I would really like to understand a bit better what the origin of this is and how this is affected in other gauge theories, because I do kind of think that, or I'm pretty sure that within the gauge that I'm chosen here, this result is independent of the dimensional continuation of the propagator. So in this sense, it's almost scheme dependent, at least with what I'm doing here. But this result can change if I'm doing different gauges, like a different than Feynman gauge. And that brings me then over to the conclusions. So I've shown you how we can potentially do asymptotic safety within a power law sensitive renormalization scheme. And we've seen that with dimensional regularization, this is possible because power law divergences are just expressed as divergences in lower dimensions. And I try to avoid the kinematic pole of the propagator by this modified dimensional continuation. So I just modify the way the propagator is formulated within the background field method. And then you see that you do see a one-loop fixed point from dimensional regularization, which is just what I talked about. And as a brief outlook, of course, I already remarked that power divergence subtraction is a really interesting scheme because it basically allows you to use dimensional regularization in quantum gravity and also allows you to do higher loop order computations. So I think what is would be really interesting to check is whether you have also a fixed point in 2-loop quantum gravity, which you can more or less easily do with this scheme. And then other questions, of course, include also what happens if matter is included, because there you already get some the one-loop non-renormalizability of the system because matter induces additional divergences. So it's not trivial to see what happens in such a system. And of course, you can also apply PDS to other non-renormalizable field theories other than quantum gravity to see whether this dependence of the power law divergences is also maybe useful for such theories. And yeah, with this, I come to the end, and thank you all for your attention, and let me know if you have any questions.
All right. Thank you, Yannick, for the nice talk. And